let's see. So this one, it's a longer problem, but I'm not sure it's as hard as it looks. So let's give it a shot. Oh, whoops, I don't want that. So the two circles intersect at A and B. Let me call this O1 and O2. So this is A and the other is B. Then we have the two lines through A. Okay, so we want to draw two lines through A that are symmetric with respect to AB. There we go. That looks a little better. And the first line cuts the two circles at G and E. So basically, I should be able to just use reflect about line. There we go. So we draw those points. So this is G and E. This is F and H. And AB is the angle bisector of that. So E is between A and G. Oh, that doesn't sound right. So the first line cuts it at G and E. So E is between A and G. How does that work? Oh, I think the lines have to be more like this. So they have to intersect that middle portion, that middle. Maybe. Yeah, how do I get? Oh, it's never going to intersect this arc unless. Yeah, oh, so something more like this, I guess. So E is between A and G. So let me delete F for now because it's causing problems, it looks like. E, how do you make E between A and G? Oh, E has to actually be, yeah, okay, like that. All right. So, yeah, that took me a while to figure that out, but that's E and this is F. All right, so yeah, let me think about how to, I want to make the intersection of these circles, yeah, bigger. Maybe something like that. Okay, so J is an intersection of EH and FG. Yeah, this diagram is too cramped. I'm going to make it better. Yeah, maybe like that. And I don't want it to look like it lies on 8B. So I like that. That looks good. So this is J. And BJ cuts the circles at K and L. So this should be K, and that should be L. And then we see, where does O1K intersect O2L? At N. We want to show the circumcircle of NLK is tangent. That doesn't sound right. Tangent to AB. Something's wrong here. We have two circles that intersect at A and B. Then we draw two lines.
A is on O1.
A.
No, K.
Okay, so we flipped K and L. And then that changes how we draw other things. So point N is the intersection of O1K and O2L. So basically like those two radii. This is point N. And we want to show the circle NLK is tangent to the line AB. That's interesting. This is a harder problem than I thought when I first read it. Let me hide stuff we don't need. Well, actually, we do want to see that whole line. Why does it do that? So we have this, this, this. Yeah. Is that everything? I think so. So we can check, is that circle really tangent? Oh, it looks like it actually passes through A. So we could first try to show AKLN is cyclic, and then we could show it's actually tangent at A. Okay. So yeah, I guess I don't need to draw this whole line then. I could just draw it up to A. Yeah. So is it an angle chase to show that NK is cyclic? Yeah, what would be the best way to show that? See, I wonder if we can somehow use projective geometry here, because since this is an angle bisector, if we draw this, we could project these through A onto something.
We should prove that O1A and O2 is cyclic. That is equivalent to showing that NKAL is cyclic.
All right. Okay, so yeah, we want to calculate the angle between O2N and O1K. Or is EF parallel to BH? Or GH, I mean?
I have a trivial observation that triangle EBG is congruent to HBF.
Oh, EBG and HPF are congruent?
Yeah, because AB is the angle bisector of angle GAH. So
Okay.
BEG must be equal to BF and BE must be equal to BH.
Ah, good
And,
point. I didn't see that.
and angle EGB is equal to angle BFH because of the cyclic quadrilateral.
Interesting. So that's probably pretty helpful. Okay, so let's see. Um, so yeah, we have that and this are congruent.
Looks like EJBG is cyclic.
Interesting.
And similarly FJBH.
I think that is because of the property of spiral similarity, taking the two congruent triangles to each other.
Okay, so they have to be cyclic because do we know that J is the intersection? Okay. So because they're congruent, but they're not oriented the same way, right? It's like, oh no, they are oriented the same way. So okay, so Khan, you're saying because those two triangles are congruent, then J has to be the center of the spiral similarity?
Yeah. Like that is just the property of the spiral similarity, I think. Maybe we can prove it by angle chasing.
Okay.
Also, GH equals GE equals HF.
GH is equal to those other.
Yeah.
Is ELFJ cyclic?
ELFJ. No, that's not cyclic. Yeah, these are hard problems today.
Mr. Michael, can you draw the segment KG and O1, O2?
Yeah.
It may be perpendicular to each other.
I think I've proved that O1A and O2 is cyclic.
Oh, really? O1A and O2?
Yes. And I know that that proves actually AL and K is also. So I will tell the angle chase.
Okay.
ABK,
Mm-hmm.
that is equal to KO1A 1/2. But okay, I didn't start in the right order, but never mind.
Sorry.
No, I think that angle trace is good, but I didn't just tell it in the right order. So KO1A,
Mm-hmm.
that is twice KBA.
KBA?
Yeah.
Well, sorry, why is that? Oh, because O is the center of the circle.
Yeah.
Okay. Yeah.
And that is twice LBA,
Okay.
and that is equal to LO2A.
Okay. So LOK is equal to LO2A.
No, AO1K.
Sorry, A, O, and K. Okay. So let me write that out.
But we need also to prove, so we have that KALN is cyclic, but we also need to prove that it is tangent.
Yeah. So I'm going to start writing up the first half, just showing that LA and K is cyclic. So angle, you have angle NO1A is KO1A. Yeah. Okay. So that's equal to angle KOA, which is equal to angle, that's twice angle K BA. Yeah. Which is equal to angle LO2A. So that means that O1N AO2 is cyclic. And then
You have a little typo, KOA instead of KO1A.
oh, yeah, it should be KO1A. Good point. And then once we know that, then angle KNL is 180 minus O1N O2, which is 180 minus O1A O2. Which is O1AK.
The angle chase that gets you that is cyclic, because we know that KO1A is equal to AO2L.
Mm-hmm.
Then we also know that O1KA is equal to LAO2.
Okay.
Basically, because of the isosceles triangles.
Okay, because O1KA is equal to O1AK,
Yeah.
which is LAO2. Okay, because these are both isosceles triangles. So so O1KA and O2AL are isosceles. So and so that means basically from the above equality. So then from the above angle equality, yeah, then we know that angle NKA is equal to angle LAO2.
Oh, and an angle chase completes the problem by proving that AB is the tangent.
Okay. Hold on just a second. So that's AKNL is cyclic. And then did we ever use that this was the angle bisector?
Yeah, we use the angle bisector to prove the two congruent triangles.
So we proved they're congruent, but did we ever use that fact in the?
Yeah, we use that because BG equals BF because AB is the angle bisector.
But did we use the fact that they're congruent in this so far?
No.
In the solution.
Yeah.
We'll use it later to prove that
Okay.
AB is the tangent.
Okay, that's where we use it. Okay. So what was your idea?
Okay, I will present it and then you can type it later. So
Okay.
apparently we have, I will prove that AK is parallel to HE.
Okay.
So AK is parallel to HE. Wait 1 second. Your configuration is a little different from mine. So we show that GBJ is cyclic.
GBJE. Okay.
Is cyclic, and we also have that we also have GBAK is cyclic.
GBAK. Yes.
So wait, let me see. We have, so AK must be parallel to HE because
Rhymes
angle,
theorem.
yeah, Rhymes theorem. Yeah, or you can just take away the angles.
Okay.
So we have AK is parallel to HE, so we must have angle, we have angle HAK is equal to angle EHA, and also angle EHA is equal to angle EBA.
Okay.
So we have angle EBA is equal to angle HAK. Then we have so apparently we need to prove that BAK is equal to ANK, right? And we have ANK is equal to AO201. And also AO201 is equal to half of angle AO2B, and it is equal to angle AHB.
Okay.
So I think I should write it out because it's a little messy.
I think I kind of see what you're saying. And then HB is parallel to AK. So
yeah, so we have
okay.
actually
So
HJ. Actually, HJ is parallel to AK.
okay.
So you can just continue the angle chasing, but I don't remember exactly. I think I should write it down.
Okay. So let's see. So we're trying to calculate KAH. I'm sorry, KAB.
Yeah, KAB. And I calculated by KAB is equal to KAF plus FAB. However, KAF is equal to AHB because of the parallel lines.
Okay. So yeah, my figure's a little different. So the way I have it, angle KAB is angle KAF minus angle FAB. So yeah, my diagram's different. But yeah, I guess in a competition, you'd have to write it both ways, but I'm lazy, so I'll just do it one way here. And then KAF is the way I drew it, that would be 180 minus AHB. So I still have to prove that those are parallel. So I'm going to do that. Let's see. Okay. And then so FAB is half of HAE, right? Or is that how you, no. Let's see. Yeah, let me just write this out. So KNA is KNA is equal to A0201. Which is half of A02B, which is angle AHB. So we want to show this is 180 minus this. How did I get something extra? Let's see. So I'm calculating KAB and KNA. KAB is KAF minus FAB. And KAF. Oh no, because AK is parallel to JH. So KAF would be 180 minus FHJ. Or AHJ. So we want to show FAB. FAB is equal to JHB. Yeah, because FAB, I think I got this. FAB is HEB. And this is 180 minus angle AHJ minus angle BHE, which is 180 minus angle AHB. So once we have all that, combining these two, so actually I didn't prove yet that KA and HJ were tangent, but I'm going to do that right now. So combining the above two of the circle NLK tangent to AB, right? So let me add in that step where we prove that HJ is parallel to AK. So since AKBG is cyclic, and also HJBF is cyclic. So yeah, what's so angle KAB is 180 minus KGB, which is 180 minus KGA minus AGB. Yeah, so KGA is KBA. Okay, so yeah, I just want to see what this angle chase is. So I know you mentioned it before. Yeah, so what is this angle chase? So KAB, it's KAG plus GAB. And KAG is KBG. Yeah, there's a bunch of stuff. So actually, let me first write that up here. B equals BH, BG equals BF. So and then angle what's the other angle that was equal? So yeah, wait, how did we forgot this? Oh yeah, an angle AGB equals BFH. That means triangle EGB is congruent to triangle HFB. Okay. I think the viewers, let's move on to the next question. I think the viewers can like try to fill in this angle chase later. But I don't think it's too hard to figure this out through the angle chase, right? The step.
I think it's actually KA is parallel to HJ, not HB.
Oh yeah, you're right, HJ.
And that is just a ring theorem, so it's not hard.
Okay. Okay. I'm going to move on to the next problem, but yeah, there is that one.
Very professionally. The proof is left as an exercise to the reader.
Yeah, yeah. Like in all the advanced math textbooks, it's left as an exercise. Yeah. So, all right. Let's see. This one maybe looks easier. It's hard to tell. So we have a triangle and a circumcircle. And then we have a point on arc BC. And it's not the midpoint of arc BC. So any point D, let me shrink this a little bit. And then we want to draw the tangent line at D and see where it intersects all three sides. Okay, so maybe I'll draw it like right here. Okay. So let's see where it intersects the three sides. We call it A prime, B prime, and C prime. A prime, B prime, and this is C prime. BB prime and CC prime intersect at E. Actually, this problem looks really familiar. I think we did this before, but we didn't solve it. An AA prime intersects the circle at F. And we want to show that D, E, and F are collinear. So I remember when we did this last, we did a bunch of projective geometry and redefining points. And I think we kind of went in a circle. But now we have a fresh start. So let's see. But yeah, we didn't solve it the first time, so. Oh yeah, it was a long time ago. Yeah, I barely remember it, but. Okay. Let me hide this. Yeah, take the revenge. So yeah, we have A prime, B prime, C prime. How do I show those are collinear? Can I use, yeah, projective geometry seems like a natural idea, but it's hard to see. Like I want to show the cross ratio dB, dB prime, dE, and something else is the same as, like if I were to project that onto the circle. So what if I take the quadrilateral ABDF and I try to project it onto B prime? So I would get, yeah, like what if I let AD intersect BB prime at a point? I feel like this might be kind of what I tried to do before, but so if I take ABDF and I project onto BB prime, I want to show it's BB prime GE. Is there something else I can project that quadrilateral through? ABDF.
Maybe through C.
Through C, yeah. So it's just, yeah, where F would go. then we would get this point. So we want to show the cross ratio of these four is the same as cross ratio of these four.
This reminds me of the proof of the isogonal line lemma.
It does look a little bit like it, yeah. So yeah, once we have these 4 points, we project through A. Well, is it the same as saying A, E, and H are collinear? I think so. No. Well, yeah, so showing that D, E, and F are collinear, if that were true, so then maybe we could define this point here. It's like B, G, E, B prime, we could project through C prime onto AD. So then we would get A, G, I, D. And we want to show that. So yeah, we want to show AGID is equal to the cross ratio of these 4 points. So I wonder if AE and H are collinear. No. Yeah, this reminds me of what I did last time when I saw this problem. I just went in circles. Yeah, it feels like there has to be a simpler way. Let me remove a couple things. Or what I could do is I could take A, B, D, F and project through point D. So onto line AB. If I do that,
Sorry, Michael, can you draw the intersection of circle A, B, B prime, and AC, and a point behind point A,
You
B,
said-
B prime? Yeah. And a point which is the intersection of AB and A prime D. Which, can you label
AB, the intersection of AB with A prime D, or what do you say?
yes, can you label it?
Oh, but isn't that C? Wait, hold on a sec.
Yeah,
You said-
I think. And ACC prime. Can you draw?
Oh, the circle ACC prime. Okay.
Yeah.
So ABB prime and ACC prime.
ACC prime, not A prime.
Oh, sorry. ACC prime.
I have an idea of using the inversion with center A power AD square.
AD squared.
Yeah, which is equal to AB times AC times AB prime, AB times AC prime, AC times AB prime, and AS times A prime, which can be worked.
Okay.
So we need to prove that D, G, and A prime A is cyclic.
Okay. I don't think that's true. Did you say DG, A prime, and A? Did I draw point G right? So it's ACC prime and ABB prime. Yeah.
Sorry, can you find the image of E with respect to the inversion? Can you find the image of E through the inversion?
Is inversion like have AF times AA prime, or is that the so what's the radius of the inversion that you want?
It's a AD square.
AD squared. Okay.
Yeah.
So I'll okay, so that's E prime.
You can delete the circle that I mentioned before
Okay.
and draw the image of E over the inverse.
Oh, the reflection of it over the inverse?
Yes, yes.
Like this point?
No, the image of E through the inversion.
Oh, it's this point. Right?
Yeah.
Yeah, it should be this point right here. Are B, D, and E prime collinear? No.
Can Pascal's theorem help?
Could, I'm not sure.
I'm not too good with Pascal's theorem, so I don't really know.
Oh yeah, Serdar is really, really good with Pascal's theorem. Let's see. So another way, I mean, we could try to show that BGEB prime is the same as BAFD. That's what we did before. You know what? Then we could try maybe let BB intersect AA prime. If we take BDAF and we project onto AF, we would get AF A prime H. And we want to show that's the same as this cross ratio. Okay, so we projected through D. Maybe we could project through B now. So AF A prime H. Is BF, let's see what BF. Oh, but then we can project through B onto the circle. So AF A prime H would go to AF CD. And then that's weird. So wait, I had AFDB. And I projected through D onto AH. And so I got AF A prime H. Then I projected through E. And so I get AFCD. I think so. I don't know why this one is so hard. It looks easy, but sorry. You guys want to check out the last problem really quickly, just to see what it is? I'm just curious. Let's see. Oh, this looks hard. I'm gonna go back.
Wait, I didn't see it. Can you just show me one more time?
Oh, this one?
Oh, yeah. But just read through it.
Okay. So we have a triangle with orthocenter H, and P is any point. Yeah, I'll just draw it up first. P is any point. And then we draw the circle with diameter AP. Okay, cuts CA and AB at E and F. So these are just the perpendiculars from P to each of them. And then PH cuts the circle again at G. And the tangent lines at E and F, I think the tangent lines, let's see, do they? So M is the midpoint of BC. And L is the midpoint of, L is on MG. So if I make P like this, L is on, so AL and MT are parallel. So here's T. So AL and MT are parallel. So I would need to draw this. And this. We want to show LA and LH are perpendicular. So yeah, it's a tricky diagram, but yeah, P can be any point. That's what makes it kind of interesting. All right, you want to move back to the last problem? This looks kind of hard.
Yeah, let's move back to the previous one.
Okay. So you keep projecting through D. What if I projected through F instead? Um, I'll just leave that there. I'll bet it has a really short solution. Because we have to use point C prime somehow. So yeah, we have B, G, E, B prime. And then we try to project through D onto the circle. We would get A, B, D, F. And then if I project through D onto A, B, we draw this point. So if I project through B, A, G, H, D, and I might get this point. So AGHD projects to C, E, H, I, C prime, E, H, I. Then that projects Is there another way to think about this? So G isn't part of the original problem. So instead of using G, could we use something else? So B, E, B prime, and some other point. Maybe this point right here. So if I label this point we want to show dB, dE, dH, dB prime is dB, dF, dH, dB prime. So we want to show that's the cross ratio BF HD. And then what can we project those through? Can we project those through A? So I kind of like projecting through A because then BF HD when we get this point. So we want to show C prime DIA is equal to BEHB prime. Okay, BEHB prime, if we project through D, we want to show that's BFHD. But if we project through A, we want to show that's CDIA prime. Yeah, so I can get rid of G in that case. Yeah, we want to show BEHB as CDIA prime. Or C prime DIA prime. Oh, do these concur here? Could be. No. Maybe there's a solution without projected geometry. I don't know. This can't be that hard. I know there's got to be a solution. That's like, let's see. Yeah, maybe Pascal's theorem, like Stefan said. So maybe we could try Pascal's theorem on A, B, D, D, C, F. Let me write this on a piece of paper. A, B, D, D, C, F. Yeah, I don't use Pascal's that much either, but can be useful sometimes. Let me get a pen. Better one. All right, so A, B, D, D, C, F. We have to figure out the right way to do this. So A, B, D, let's see. What if I did it like this? So A, B, and D, D meet at C prime. A, F, and C, D. No, we don't have that. We want A, F, and D, D. So what if we do it like this? A, D. So A, F, and D, D meet at 8 prime. And then A, C, and B, D meet at a point. A, C, and B, D. And then C, D, and B, F. Or we could do it like this. There's so many different ways to do Pascal, that's the thing. BD and BC. And then AD and BF. So yeah, there's so many different ways you could do Pascals on this, but what if I drew this point right here? Those almost look perpendicular, but I doubt that's true. Yeah, so let's see. DD and BC, so A prime, and then BF and AB. A prime G and AC and DF. Yeah, I don't think this is gonna. So these 3 points would be collinear by Pascal. A prime, J, and G. But I'm not sure if that really helps. Maybe it would let us use, I don't know, projective geometry somehow. Let's see. Is there another way we can use projective geometry? AF and CD, and then DF and BC. Yeah, there's like lots of ways to use Pascals. So like, yeah, I just don't know really what's the best. Yeah, we started like 5 minutes late, so if we go over like 3 minutes, it's okay. Let's see, let's try to get point E involved. So E, yeah, H wasn't part of the problem originally. Okay, what if we do it, okay, let me try Pascal's this way. So we want DF and BH. And then AH. So yeah, we want BH and DF. And then AH. Oh, you know what? Yeah, AH and BD. So that would be I. And then BD and AF. So if BD meets AF at a point, those almost look parallel, but let's fix that. Then this point should be collinear with I and E by Pascal's. So maybe that helps. Yeah. So yeah, if we can show I, E, and J are collinear, that also solves the problem. It's like, yeah, it's equivalent. Oops. Yeah, it's hard to do a diagram where you can see both, but I'll try. Yeah, it's really, yeah, what if I just forget about A prime? If I can show that I, E, and J are collinear, that solves it. Maybe I use like Pascal's again or something. All right, I think I'm gonna stop here. This was a tough session. So I think we only solved 2 of them, right? So yeah, it'll be fun to go back. We made some progress. We noticed a lot of things here. This one we solved pretty quickly. This one, yeah, we were still working through. These are a lot of good problems. Yeah, so I encourage, this one we actually did end up solving. But yeah, for anyone watching, I encourage you guys to keep working through this, and like all the people in the session too. So thanks everyone for participating today. Even with daylight savings time, thanks for doing it a little earlier. It was a lot of fun. So if you're watching and you want to join the future sessions, feel free to email me at mgreenb801@gmail.com. It's in the description of the video, and we meet at 8 a.m. US Central Time every Sunday. Thanks and have a great day.